Now that we know what the transaction manager can see, namely transactional begin and end and read and write, let's talk about what the transaction manager needs to guarantee. There are four basic properties that the transaction manager guarantees, which are known as the ACID properties: atomicity, consistency, isolation, and durability. And before we go into each of them, I want to emphasize that together they're a way of remembering what we need to know about transactions. They're a mnemonic device. They're actually not in any way a formalism, so they're not, for instance, axioms in some axiom system, the way Armstrong's axioms were. These are just sort of ways for us to remember the basic ideas that we want to guarantee with transactions. We'll have formalisms for some of the transactional guarantees shortly. Going through these, let's begin with atomicity. Atomicity is the all or nothing property. All the actions of a transaction should occur, or none of them should occur. At least that's how it should appear to anyone who is outside of that transaction. Consistency is the property that if the database starts out in some state we define as consistent, it ends up in another state that we define as consistent at the end of the transaction. Isolation is the property that the execution of each transaction is isolated from that of the others. So if you're a programmer who's composing the code for one transaction, you don't have to think about any other transactions running in the system. Basically, we hide concurrency from the programmer, and that's the idea of isolation. And then finally, durability. If a transaction commits, its effects should persist in the database. So if the database system tells you that it commits, then you can be guaranteed that the actions you took in that transaction will persist. Let's go through each of these in a bit more detail. We'll start with isolation, actually. We'll start with I because it's the one we've been talking about the most. It's the issue of managing concurrency. Remember that the database management system is going to interleave the actions of many transactions, where actions are reads and writes on the database. And the database's job is to ensure that two transactions do not interfere with each other in some way. So each transaction is going to execute as if it's running by itself. The concurrent actions of one transaction should not affect another transactions. And the net effect should be identical to executing all of the transactions in some sequential or serial order. Okay, so even though we're going to have concurrency, we should have an effect that basically looks like a sequential ordering. This is going to allow users and programmers to think about their transactions in isolation without considering the effects of other transactions. Let's look at an example. We have a transaction here, T1, which is going to transfer $100 from R to S. We've seen this example before. We're going to have another transaction, T2, that is going to read the value of R and then print the values of R plus S on the screen and end the transaction. Now, of course, the database only sees start transaction, read, write, and end transaction. It doesn't see the arithmetic and it doesn't see the print statement. But let's think about how these two transactions interleave. If T1 starts and executes steps 1 through 4, we've debited $100 from account R. And then T2 starts, it's going to read the value of R, which is $100 short. And it's going to print the values of R plus S, which is the total of the two, which is going to be missing $100 right now, and end the transaction. And then finally, T1 will finish its job. It will add the $100 to account S and finish. And so what we're seeing here is an inconsistency. T2 is seeing a state of the database that is not isolated from T1. T1's actions are visible to T2 in a transient way. Okay, and that's the kind of isolation we want to provide, is to avoid these kinds of problems. We'd like T2 to either have the effect of looking at the database before T1 runs or after T1 runs. So that isolation is what we're going to try to achieve. Two properties that go together are atomicity and durability. And to talk about them, let's talk about what happens at the end of a transaction. Transactions end in one of two ways. Either the transaction commits, so there's a request from the transaction to commit, and the database system agrees to commit and calls back to the transaction with an agreement to commit. This happens after the transaction's completed all of its actions, and if the database guarantees that it will commit, that is a contract with the application developer, that the application no longer has to worry about this transaction. It is for sure going to commit and be durable in the database. The other possibility is that a transaction ends in an abort, either because the application requests one, the user cancels the transaction, or because the database system is unable to commit the transaction for some reason. For example, it might crash or it might run into software problems. Okay? In either of those cases, the transaction does not commit, and the caller should assume that that transaction is as if it never happened. So the two key properties for this transaction are atomicity, the all or nothing property that either the transaction commits or it aborts, and durability, that the effect of a committed transaction has to survive any failure of the database. The way we're going to achieve atomicity and durability is we're going to use a log. the database is going to write down in a log all the actions of a transaction. And for aborted or failed transaction, it's going to undo those actions. And for committed transactions after a crash, it's going to redo those actions to make sure that they're propagated to the database after the system recovers. So let's look at an example. Here we have a transaction on the right. Once again, we are transferring $100 from R to S. In terms of atomicity, if the transaction fails after step 4, but before step 7, there's $100 missing from the sum of R and S, and we certainly don't want that $100 to disappear. So if the transaction fails between 4 and 7, either because the user aborts it or because the system fails, then the database must eventually ensure that the updates of this partially executed transaction are not visible, are not reflected in the database. Now the durability property, if the transaction runs to completion and in step 8 says end transaction and receives a commit message, then the user should rest assured that their 100 or perhaps it's $100 million were transferred from R to S. Consistency is the fourth of the properties in ACID and maybe the one that's the least well defined. The idea is that a transaction should take the database from one consistent state to another consistent state. So how do we define a definition of consistency? Well, that's a bit database dependent, but we'll assume in a relational model that consistency is defined by a set of declarative integrity constraints, which we have in create table or create assertion statements. These would be constraints like primary key constraints or type constraints or functional dependencies like keys and foreign keys. Okay, so these kind of integrity constraints state how the database must be at any given time, and a transaction that violates these integrity constraints will be automatically aborted by the database system. All right, this is the only kind of consistency the database understands, are these integrity constraints that have been registered with the database system. So these are the things it will check at the time of commit, and if the transaction violates an integrity constraint, it cannot commit. So in sum, we've seen an overview so far of transactions. ACID transactions make the guarantee that they'll improve performance via concurrency and relieve programmers of correctness concerns with respect to both concurrency and failure handling. And there's two key issues that we considered with mechanisms that go along with them. The first issue is concurrency control, and we'll learn about how that's done with two-phase locking. And the second is recovery, and we'll learn about how that's done with write-ahead logging, or WAL. In the next slides, we'll focus on concurrency control, and then we'll move towards recovery.